Hello, everyone. All right, welcome back. All right, now we're going to be looking at the next section where we're going to calculate more limits. So when we originally looked at this first example, sorry, hope I'm not making a mistake. When we looked at this first example on page 3, I talked about how if you substituted the number 1 into the function and evaluated the function at our limit number, the answer is what the limit ended up equaling. So we said this is a polynomial function, it's continuous. So the limit of the function is the same as just substituting in our limit value into the function. But then I said we can't assume this. So there are a whole bunch of proven rules about limits. So I'm going to fly through these fast because hopefully most will make sense. Okay, so the first rule is if you are taking the limit of just a number, then the limit is that number. It doesn't matter what a is. So the limit of 5 is just 5. It doesn't matter what number you're approaching. The limit of 3 is just 3. It does not matter what x is approaching. The limit of 7 is just 7. It's just a constant. Okay? So if you are finding the limit of a constant of a variable, it just equals that answer. It equals what you are approaching. So pretty much you just substitute in your number a that it's approaching, substitute that into the function. So the limit of function f, or function x, as x approaches -7 is just -7. The limit of x as x approaches 8 is just 8, just substitute it in. The limit of x as x approaches -0.4 is just -0.4. Okay? Now, a whole bunch of rules exist if we're talking about two different functions. So if the limit of function f exists and the limit of function g exists, then the following rules apply. There are sum and difference rules. So if you are taking the limit of two functions that have been added together or subtracted, you find the limit of the first function, the limit of the second function, then add those together. All right? So the limit of this function that says x minus 6, as x goes to -1, you could break it up into just the limit of 6, or I'm sorry, the limit of x as x approaches -1, and so then subtract the limit of 6 as x approaches -1. So the limit of a constant is just what your value of a is, and the limit of a number is just that number. So this gives you a total of -7. All right, so if you tried this, so really you can break this up into two pieces. You can rewrite this because we want the limit of a sum. You can rewrite it as the sum of each individual limit. Now, do you have to rewrite it? No, because we're eventually going to be taking a bunch of shortcuts. So the limit as x approaches 4 of the number 3 is still the number 3. And the limit of 2x as x approaches 4, you can substitute your 4 in there. It's just going to be 2 times 4, which is 8. 3 plus 8 is 11. So your limit is 11. All right, it works the same for multiplying. If you are taking the limit of a product, it is the same as the product of each function's individual limit. All right, so if you're taking the limit of 7 times x, you could break that up into the limit as x approaches 5 of 7 times the limit as x approaches 5 of x. The limit of just a number is that same number. The limit of a constant is your value of a. So then you multiply those individual limits and you get 35. Now notice if you just substituted 5 in there, 7 times 5 is 35, and the limit of a number is that same number. So again, they're shortcuts. So they're shortcuts because all these rules exist. All right, so here we have a product. You could break it up into the limit of 3 as x approaches 5 times the limit of x squared as x approaches 5. The limit of 3 is just going to give you 3. The limit of x squared, you just substitute in your 5. So 5 squared is 25. 25 times 3 is 75. Easy. Pretty much you right now are just substituting in your value of a and evaluating the function at that value. All right, quotient rule. Pretty much the same thing as sum, difference, and product. If you have the limit of a quotient, you can break it up into the limit of your first function divided by your limit of your second function. Now that only works if the limit of your second function does not equal 0, because then you're dividing by 0, and that does not exist. All right, so the limit of this quotient, you can break it up into the limit of the numerator over the limit of the denominator. Well, here's a constant, so that is just going to be -4, and here we have a number, so the limit doesn't matter what number we're approaching from, it's still that same number. You end up with -2. All right, so same thing if you had just substituted -4 into the problem in the first place. -4 divided by 2 is -2. And again, we can take these shortcuts because all these rules have been proven. So the limit of this quotient, pretty much just substitute in your 3. It's going to be the same as 3 squared over 7, 9 over 7. That's it. That's what your limit is. All right, flip, a whole bunch more rules. A polynomial rule is, this was our first example we did together in back on page 2. So you can just simply substitute in your a straight into the function. So if you're taking the limit of this polynomial function, you're just literally substituting in 2 for x and evaluating it. If you have a quotient, then again, we have a rational function. You literally can just substitute a into your function. All right, so take 8, substitute it here, substitute it there, follow your order of operations. 8 squared is 64, 2 times 8 is 16, 64 plus 16, and then you divide that answer by 8. That gives you 80. 80 divided by 8 is 10. All right, there's something called the equal function rule. If one function equals another function, then their limits are going to equal each other. All of this should make sense. You don't have to know any of these rules by name. You just have to apply them, apply the rules. All right, power rule. So if you're taking the limit of a function to a power, it is the same as taking the limit of the function, getting that answer, and then raising that to the power. Here's what I mean. If we want the limit as x approaches 3 of 2x minus 4 raised to the 5th power, you can simply find just the limit of this linear function, substitute your 3 in. 2 times 3 is 6. 6 minus 4 is 2. And then raise that to the 5th power. 2 to the 5th is 32. So again, you are literally just substituting in our value of a into our function and then using order of operations. All right, there's an exponent rule. If b is greater than 0, your base, then the limit of that base raised to a function as x goes towards a number is the same as the base of the limit of your function. Sounds a little weird. Again, you're just literally substituting in the number you're approaching into the function. So if you want the limit of 2 to the x as x approaches 3, it's really 2 times the limit of x as x approaches 3. When you take the limit of a constant, it just equals that number you're approaching. 2 to the 3rd is 8. You can get the same results by just substituting in 2. Substituting in 3 in for x. There's log rule. if your base is greater than 0, if b is greater than 0 with b not equaling -1, then the limit of a log is the same as if you found the limit of the function first and then kind of substituted that back into your log function. And logs are only defined on positive numbers, so the limit of your function has to be a positive number or the log won't exist. So, for example, the limit as x goes towards 9 of log base 3 of 9x. We can just find the limit of 9x first as x goes to 9. So, substitute it in, 9 times 9 is 81. And then you're finding the log base 3 of 81, which remember you're saying 3 to what power is 81? And 3 to the 4th power is 81. Alright, so now it's time to kind of practice. So for most and or all of these, you are simply substituting in the number we're approaching into the function. That's really all you're doing. Alright, so this limit is going to be the same as if you just evaluated the function 5 times 2 minus 1 and take the square root. 5 times 2 is 10. 10 minus 1 is 9. Square root of 9 is 3. So the limit of this function will approach 3. Alright, for b, we are going to do the same thing. Substitute in your 3. So 5 times 3, add 10, take the square root. 15 times 15 plus 10 is the square root of 25, and that is 5, so the limit will approach 5. Whoops, sorry, can't see what I'm doing. Alright, so it's pretty easy. You just substitute in x. Alright, the limit as x goes to 1 of 3 of x squared plus 1. So you are just simply evaluating 3 raised to the 1 squared plus 1 power. 1 squared is 1, 1 plus 1 is 2. This is the same as saying 3 squared, which gives you 9. So your limit is also 9. Alright, the limit of 4 raised to the power is, and x is going towards 1. So we are just going to just substitute in 1 for x. 1 plus 1 is 2. 4 squared is 16. So your limit also is 16. Let's try some log ones. Alright, the limit as x goes to 2 of log of 3x to the 5th plus 4. First, you're just going to substitute in your 2. So we're going to figure out what is 3 times 2 to the 5th power plus 4, and then take the log of that. Alright, 2 to the 5th power is the number 32. Again, I'm following order of operations. 3 times 32 is 64. 64. Oh, no, I multiplied wrong. My bad. 3 times 32, you are allowed to use a calculator right now, is 96. 96 plus 4 is 100. So we are doing the log of 100. And remember, if you don't have a base, it's invisible. It's base 10. So 10 to what power equals 100? 10 to the 2nd power. Alright, try this one. We're doing another log. So we want to know what's happening as x approaches 5. 2 times 5 is 10. 10 minus 1 is 9. Log base 3 of 9. 3 to what power gives you 9? That answers 2. So the limit is 2. Alright, if you're going to do limits involving some trig functions, there are 3 of these that you do need to have memorized. Okay? So some of these should make sense. Alright, the limit of the sine of x as x goes to 0. Think about when x is 0, which is over here, that's the coordinate 1, 0. Sine is 0, so your limit is 0. Cosine, as x approaches 0, cosine is x is 1. Okay? Now technically this function's undefined as x goes to 0 because we know that the limit as x goes to 0 of sine of x is defined to be 0. But then when you substitute